Hello and welcome to Erudite. In this video we're going to continue looking at the kNN algorithm. So let's get started. Well, before we use this Jupyter Notebook interface, I just want to show you a little bit of the setup so that you can follow along. And all the files that we're going to use I'll post on GitHub, that we're going to be using quite a famous dataset. So within my machine learning folder, I just made a little folder called kNN. And I've put a CSV file with some iris data, and we'll have a look at that in a moment. The iris analysis Jupyter Notebook file, and there are many videos about how to install a Jupyter Notebook IDE, so they're well worth looking at, and it's a fantastic tool, and hopefully you'll see why in a moment. And something called kNN modules, and this is nothing spooky, it's this file here. And if you saw my previous video, you should recognize both of these functions as we wrote them in that video. This is the one for measuring the Euclidean distances between points, and this is our kNN algorithm. Now, all I did was put them into a single file, which I called kNN modules, and now we can use that as an import into the Jupyter Notebook. I do want to make one brief change here, however. I really like this, where I can print out the list of neighbours that were found closest to the point and look at their outputs. But I don't always want that to happen. So what I want to do is create a little flag here that I can set. And I'm going to set it equal to false by default. But if I change it to true, if show neighbours, then we can print out that list, so I can select if I want to see them, which can be really helpful when debugging or seeing how accurate the data is. So now we've got this little file set up, we can save that. We'll close it for now. We might come back to this, but we'll close it for now, and we'll go to the Jupyter Notebook. Now I will just explain that in here, when you run this, it'll open up, and it'll actually open up on the main page like this, and I just navigated to the kNN, and then you click on here and it will open up the notebook. And normally this is completely empty, but I've just populated a few cells for a little bit of initial data analysis before we dive in to the kNN part. So let's have a look at what these do. Well, the first one, it imports a bunch of libraries that we're going to be using in this tutorial. The pandas one is basically just to manipulate the CSV file and pull out some of the data. We're going to use Seaborn and Matplotlib to present some of the data in graphs, and we've got the kNN modules that we've previously made to use, and random, well, we'll have a look at that later. And this is just to get the plot, the Matplotlib plots, to have a style with the dark background, because I prefer it. So let's run this, and it'll take a moment or two as we import all of those libraries. But while that's doing that, we'll just talk through this. So down here, we're creating a data frame, a pandas data frame, and all we're doing is using the read CSV function to pull the data from that iris.csv file. And in fact, let's have a look at that data frame. We'll have a look at what it looks, its shape first. So we'll run that, and we can see that it's got 150 entries, so it's not a huge data set by any means. And we have these as our headers: sepal length, sepal width, petal length and petal width, because we're going to be looking at the iris flowers. And if we have a little look at some of the data here using the .head function, just gives us by default the top 5 results. These are all iris setosa, but we have two other types of iris species in there. We have the virginica and the versicolor. And so I've split this data frame into 3 that are for each of these species, and that's just for when we come to pass training data, or we pass known data to the kNN algorithm. So we've had a brief look at that, and it's handy to keep this up so we can have a look at these titles. if we want to pull the column names to get information. And with these three species types, we're basically going to be using the kNN algorithm to see if we can predict a species, giving the algorithm a sepal length, sepal width, petal length and a petal width. Let's just plot some of this data, and we can have a look here and see that I'm initiating a figure using the plot.fig command, and I've just set the size because it's quite nice to have a slightly bigger plot for this. And then what we're doing is we're just overlaying, well, we've set the labels up, so this is all just basic setup for a graph here. But we're using a 3D graph, so we've got an X, Y and a Z, and we've got the values from each of our data sets for the Setosa species, the versicolor and the virginica species. And we're just going to plot them on the same plot with different colours, where the Setosa would be azure, versicolor cyan and the navy virginica. So let's have a look. We have these really clear domains for each of the species, where we've got the Setosa down here in the azure, the versicolor here in the cyan, and the virginica up here in the dark blue, like navy blue. So you can immediately see from this data that we have three distinct domains, and that we should be able to, if we placed an unknown point in one of these domains, predict it quite easily. So let's insert a cell below here. Now what we're going to want to do is just have a little think about the process. So we need to prepare the data for our kNN algorithm. Because if you remember, it takes things as a list or a tuple, it can do that too. So we want X to be equal to the sepal length, Y to be equal to the petal length, and Z to be equal to the petal width. And we want a list of known inputs as that list, X, Y, and Z. And the known outputs as numbers, because at the minute the known output says it's either an iris Setosa or an iris versicolor or so on. So at present the outputs are iris Setosa, iris versicolor and iris virginica. We want to change this to 1, 2 and 3 respectively, so that our output will tell us 1, 2 or 3, and then we can convert that back to whether that means Setosa, versicolor or virginica. So let's have a look at how we can do this. Well, first we'll initiate some lists. So known inputs equal to an empty list, and our known outputs equal to an empty list as well. And then we're going to create a little dictionary to help us switch the species to number. So what we want to do is iterate through the data frame and basically just put the X, Y, Z values into the known inputs and put the output, the species identifier, in the output. And so these are index aligned. We'll just run through and do it the same. So for index row in div, and we'll use the iterator function, we can go known inputs dot append. So we're adding into that known inputs, and this is going to be a bit busy, but effectively we want the column names, so sepal length, petal length and petal width, wasn't it? That's what we wanted. Sepal length, petal width. Yes, lovely. Okay, so we need to make sure we get those names right. And then we want to have known outputs dot append, and we're just going to use that species to number dictionary, and we'll pass into it row species, so that whatever label it picks of these, it'll then just store the number 1, 2 or 3. And we can check this by printing a few of them out. So let's print known inputs, and we'll do the first 5 values, and known outputs 0 to 5. There we go. So let's just run this cell, and we can see, because obviously the first few there, it's in order. I think there's 50 Setosa, 50 versicolor and 50 virginica. So the first 5 are all Setosa, 1, 1, 1, 1, and then we've got this X value, which is the sepal length, Y value, the petal length, and Z value of the petal width. We now want to go, and I would like to sort of get some test points. So we're going to test our kNN value, but first I want to make a pretty graphic or a pretty image where we can show where the test point is. So I'm copying that graph setup here, and I'm at the top just going to put sepal length, and to begin with we'll just have a look at it being 5 centimeters, petal length at 2 centimeters, and petal width being at 0.5 centimeters, and that should give me a Setosa, I think. And what we want to do is add into this that extra data, so we'll have an x3, y3, z3, because I'm feeling imaginative, and this is just sepal length, petal length, and petal width. And then we want to show this on the plot, so we add an extra point down here, scatter 3D, x3, y3, z3. We'll keep it same S value, and we'll give it a really bold color so we can't miss it, of red. And that is our test point. So let's run that and see what we get. There we go. So that's the point we've just made up. It's a completely made up point, and it should, our kNN algorithm, when we use it, should predict that that is Setosa in this Azure set down here. So let's set up that prediction now. So we'll test the kNN prediction. Test is equal to x3, y3 and z3, and we're just going to use the imported kNN algorithm from that module set. So kNN underscore modules dot, and I think I called it just kNN all capitals in there, and we've got our test value. And did we call these just known inputs up here? Yes, known inputs and known outputs. Nice and simple. Known inputs, known outputs. And I'm going to use a k value of 5, I think. And we'll make sure we can see the neighbors as well. So let's run this. And oh, I didn't tell it to print the prediction. Actually, in Jupyter Notebooks, you don't need to, if you're just putting something at the end, you don't need to add in a print statement. So we can see that it's predicting 1. If we scroll up to where we had decided which would be which, Iris Setosa is 1. Or here, 1 Iris Setosa. So it's predicting that one correctly. Let's just check a few more while we're at it. We'll have one for the versicolor, so we'll change that to 6, 5 and 1. Let's run this. So there's our point now, right in the middle of the versicolor one, so it should predict that that's a 2. There we go. That's working beautifully, and we'll just try one more, which is 7 here, 6 and 2, and that one should evaluate to be the Virginica. There we go, that's where the point is. There we go, beautiful. So I want to show you something that's really, really cool, that we can now map how the kNN algorithm is interpreting this three-dimensional space. So we can basically look at the domains where if you have any point in that domain, it'll tell you that it's setosa, or if you have any point in another domain, it'll tell you it's versicolor. So let's code this up to generate a three-dimensional plot that shows these domains. So we'll start by a little comment, making a 3D map of points for the kNN algorithm domains. And we're going to want to split things up a bit. So we're going to have setosa X, setosa Y and setosa Z. And they're all going to be empty sets for now, because these will get populated as we carry out our predictions. And then what we want to do is create a set of values that we're going to iterate over for the x's, the y's and the z's. And this is effectively the limits of the three-dimensional plot that we want to explore. So what I think it's quite good is basically to consider between 4 and 8, 1 and 7, and 0 and 2.5. And I think I'm going to keep them quite small, these steps between the values. So let's have our x is equal to 4.0 plus, and we'll split it into little 0.2 delineations. So we're going to need 20 of them. In range 0 to 21, because to get to 8 obviously we need 20. 0.2 equals 4, so 4 plus 4 is 8. Lovely. Y's will be equal to 0.1 plus, and we'll keep it at 0.2 delineations or separations again, in range 0 to 31. Because it's got to go up to 6, so well, this has to equal 6 for that to be 7, sorry. And the z's are going to be equal to 0.0 plus, and we're going to make this 0.1 because it's a much smaller set for z in range 25 of them, so up to 26. There we go. Now that maybe didn't make sense to begin with, so hopefully this should enlighten you a bit. For x in x's, for y in y's, and for z in z's, we're going to carry out the prediction. So this is just iterating over all the points in that grid and carrying out a kNN prediction. The reason we can't just do this with the in range is because the in range function doesn't work on floating points, or it has to be integer values for range to work, or at least I believe it has to be. If I'm wrong there, please correct me. Prediction equals kNN underscore modules dot kNN, and then we have the x, y and z. So these are coming from these x, y and z. So what you do is you're iterating through the z list, and then you move one on y, iterate through those. So it's just slowly iterating through the set, and we're going to use our known inputs and our known outputs, and we'll stick to using 5 at the minute as the neighbours, our k value for neighbours. And then really simply, we're going to say if prediction is equal to 1, and this is where it gets a bit tedious because we write this out a bit, we are appending these values to each of these points. So what we've done now is created a set of values where for any point in the grid, it's going to say whether it's setosa, versicolor or virginica. And it's also, the reason I've sort of prepared it in this format of the X, Y and Z is so that we can use it within the plot type that we'd used before. So let's go and grab, or let's run that. That might take a moment to run because it's just, yes, you can see here, it's just the star means it's not finished yet. It's running but not finished, and now it's done. And what I want to do is come and grab this. We'll grab the lot and then sort it out. So we're copying, pasting that down here, and we're going to want to get rid of all of these because we've already got our X, Y and Z assigned, and we don't have a test point in this one. And these we're just going to switch out for setosa X, setosa Y, setosa Z. And I actually think that it might be a bit big to have this size parameter as 50, so we'll drop that to 10. Let's run this and see what we get. So you can see that we've got these domains, but this doesn't look so pretty because it's a bit tricky to see each individual one. What's quite good is we can comment these out, rerun this, and you can select to see specific domains. So anything in this space will be predicted to be versicolor. And this is a really, really helpful way of looking at how your kNN algorithm might be misinterpreting data or misassigning regions. You're missing out the middle ones. You can see the domain. But this can be really, really helpful because if we have a look back at our data here, you can see that it's fitting, it's very strongly suggesting that this is all blue and this is all blue, and that this is all setosa and this is all setosa. So it's confidently fitting things well outside the domain of our data, and that's something we always have to be very careful with when we use machine learning to try and give us insights. It isn't really suited to giving us insights outside the domain of our training data, and that generally is the case for all forms of machine learning. I think we've explored what we can do with three-dimensional data, so let's have a look at exploring 4D data. And it's really important to note that we can't use 3D graphs to visualize our data very easily. Let's put it that way, because you can always split it down into chunks and sections where you're looking at 3 variables at a time, but that doesn't give you the picture of the whole data. You can go into cell and you can change your cell type to markdown, and then it just is a text cell, so that can be nice. Previously, we've been testing whether our kNN algorithm is doing okay by choosing a point and seeing where the point is on our 3-dimensional graph and going, okay, so I know what it should be, either setosa or whatever. Has it predicted that? Well, we can't do that with 4-dimensional data because I can't just look at it and tell you where it should be. So we're going to have to think rather creatively of ways that we can use our data to help test whether the kNN algorithm is giving us valid and useful results. But first, let's get our data. So known inputs, and we're going to call this 4D, and we'll make that an empty list. We'll just do the same thing we did before for index, row in, and we, oh, I can type, I promise. Then our known inputs 4D, append, and we're just going to add, I'm just going to copy and paste the chunk from above. We wanted to add the sepal width. Lovely. So that should give us our 4D data. Let's just check that that's working by printing out known inputs 4D, and we'll just have a look at the first 5. Yes, there we go. So we're getting our nice sets now that have 4 variables involved. We're going to use a chunk of our data to test how well our algorithm is performing. So we save a bit aside where we know what the outputs for those values are. We create our kNN algorithm and the prediction tool, and we make predictions for those points. And we see if the predictions match the known output. And we can use that to get an accuracy value. So what we're going to do now is define a couple of functions. We're going to define one for how to get our accuracy from a test set. And we're going to define another that will allow us to split our data into a test and train set of data. So let's start with the first one. We're going to have an accuracy function. We'll take a test set and perform prediction comparing to a known output, and we'll return a percentage accuracy. Full stop. Okay, so how are we going to do this? Well, let's define the function, define, and we'll call it accuracy, and it's going to take a test set of inputs and test outputs that it needs to compare against. It's also going to need a training set of inputs and a training set of outputs, and we're going to need a k value because that's what we're going to, when we run the kNN prediction, we're going to need that k value as well. Now it's very important to note that kNN doesn't involve training anything. This is just pinching some terms from other parts of machine learning. We just use those training sets to measure our distances. We don't actually train like a neural network or anything like that to carry out this intelligent behavior. So let's start by initiating a count, and we'll set it to 0, and every time we get a correct prediction we'll add 1 to our count, and then we'll compare our count to the length of our test inputs, so we can divide it by the length of our test inputs and then times it by 100 to get back a percentage, because if all of the inputs work, it predicts correctly, then the count value will equal the number of inputs. Okay, so for index test and we'll enumerate the test inputs. If kNN modules dot kNN test, we're taking our test value from here. Let me just move this up a bit so it's easy to see. We're taking this test value. So if in here there's tons and tons of test values, we're taking just one of them for now, running it into here and going test the train inputs, that's our known inputs, and the train outputs, known outputs, and we're going to want the k value. If the prediction from this, so if this whole function returns a value that's equal to our test outputs at that index position, then count plus equals 1, because it's correct. It's predicted the correct value. And then at the end of this whole thing, we're going to want to return count divided by the length of the test inputs. And because we want it as a percentage, we'll just multiply it by 100. Okay, so we've got our accuracy function, but you can see we've got these test inputs and train inputs and whatnot. So we've got to have a way of splitting our data. So we're going to describe this as a function to create the test and train sets. So we're going to just define test train, and it's going to take the full inputs, so that's just all our known inputs, and the full outputs, all our known outputs, and it's going to take the percentage of values that we want to save for testing. So if you say 20%, it will make sure it takes 20% of the full set, or the full inputs and full outputs, to use for testing. And we're going to need to initialize all of those things that we're going to have to return: test inputs, test outputs, train inputs, and train outputs. And we're just going to initialize them as empty lists for now. There we go. So we need to know how many of the values, so what number of objects are going to have to go into the test inputs and test outputs set. And then whatever's left over goes into the train inputs and train outputs. So we're going to have the number of test objects, or number of test elements, that's going to be equal to the length of the full inputs divided by 100, and we're going to want to multiply this all by the percent that we've selected here to be our percent test. So if it was 20%, we've divided that lot by 100, now times it by the percent test. But I don't want this to be a float, so I will make sure this is an integer value by using the int function. So it's no good just taking the first bunch of values and always picking those to be the test values. We want to add a certain level of randomness into this. So we randomly select a bunch of indexes or indices and use those positions. So every time we're getting a different training set. So we're going to use the random function. Remember, we imported that right up here, this guy here, and we're going to use that now. So I know it's been a while, you've stuck with me, and we're going to use it. So random index is equal to random.sample. I should really call that random indices. Random sample, and this is just a function that allows you to get a sample of values in a given range that is taken from, so you say how many samples you want and the range that those samples must be. And it doesn't have duplication either, so these are each unique values randomly selected. So we're going to want range 0 to the length of the full inputs. So it's picking any value in that range. And how many of them do we want? Well, we want the number of test values. And then for index item in enumerate full inputs, if the index is in the random indices, then this is one of our test values, and we need to store it in the test value thing. So test inputs dot append, and we'll add the item, and test output dot append, and we'll use the index to get that value. So if the index is in the random indices set, so this randomly selected bunch of numbers that gives us the percentage chunk that we want, it'll store it in the test inputs and the test outputs lists. But if it's not, else, we're just going to use the train set. It'll just go into the training set, and they're the normal ones that we'll just use for setting up the kNN algorithm. Train outputs. And then after we've done all of that, we return this set of lists. Right, let's run that and then we'll test it. So we're going to get the test and train sets. So I'm going to say test inputs. Let's just grab this because typing is tiring. Equals test underscore train known inputs 4D known outputs, and we want, let's say, 30% to be used for the training. So 30% for the testing, and we'll have 70% for the training, or that we'll use when we do that distance calculation for the kNN algorithm. So let's print test inputs, and we'll have a look at the first bunch of those. So they're all Setosa because that first 50 or so is Setosa, and they're all different. Let's run it again and see. Yeah, we're getting changing values. Great. So the randomness seems to be working, and we're able to split our data into a test and train set. So now we want to test the accuracy. Let's use that other function. So test accuracy of the kNN algorithm. We can say accuracy, or the ACC, is equal to test inputs, test outputs, train inputs, train outputs, and we'll stick to 5 for now, and then we'll want to print that out. So using 70% to run the algorithm and 30% to test it, we're getting a percentage accuracy of 95% or 96%, which is absolutely fantastic. But I mean, if we look at the 3D data, it's quite nicely organized into domains. There isn't a huge amount of overlap, an area where you're likely to get a lot of misassignment. But it's really nice to see that we can now start to put a number on how accurate this algorithm is. So the question is, can we optimize to find the best k value? I'm just going to pause for a moment and see if you can think of a way of using the tools we've developed here to find an optimal k value. So let's have a look at how we can achieve this. Well, I'm going to start by initializing a couple of lists. K-list, which is going to keep track of our k values. An accuracy list, which is going to keep track of the accuracy of the performance of the algorithm as we alter the k values. And we're just going to have an index list because I'm going to turn this into a pandas data frame so that we can make a nice seaborn plot out of it. And what we're going to do is iterate through a set of k values, and we're going to perform the prediction multiple times for each k value, so we can get a bit of a data spread and see which k value gives us the best accuracy. So let's start. We need to have a count is equal to 0, because we're going to use that to basically add to our index. For I in range, we'll run 30 of each prediction. Doobie doobie doo. Will be equal to test train, so we're using that function again. Known inputs. So remember, because it's randomly selected, we're going to get a different set each time of testing ones and training ones. And we'll use 30% of the data each time as well for the testing. For k in range, and so we'll go up to 15. So from 1 to 15, the k values. We want to record the accuracy, the test inputs, test outputs, train inputs, train outputs, and the k values. So each time k changes, we're getting a different k value going into here, giving us a different accuracy reading. And we're going to append that to our list. So our k value, k list, accuracy list, append the accuracy, and we're going to have our index list count, and then we'll add 1 to the count for every single value that goes in. So what happens here is that we're basically just iterating, we're populating these lists with a whole load of k values. For each k value we're getting an accuracy, and we're doing multiple repeats. We're doing 30 repeats of this process so that we get 30 data points for each k value, because otherwise we might, just hit it lucky and get a particularly good k value on one value just because of the test and train set that was selected. So this helps smooth out those problems. And then what we want to do is, I just want to prepare these as a pandas data frame. So don't worry if you don't understand this bit of code, but I would suggest, if you want to get into machine learning, to really get familiar with certain libraries like pandas and NumPy particularly, because they're incredibly useful just for representing information. I've deliberately avoided them for this series, because I just thought it might be an overcomplication if you're starting out. But it's also quite nice to code things from a very simple set of rules, because you have to really understand them. So what we're doing here, is we're creating a pandas series of k values and accuracy values where they're indexed to the index list, so everything's nicely lined up. And then we're just going to create a dictionary which will convert into the data frame. So k value, and we're going to call that to k values, and the accuracy to accuracy raw, and then ka equals pd dot data frame ka dictionary. So the ka here, just means k value accuracy, or I could have called it kva. I just thought ka sounded all right. So we'll run this, and let's have a quick look at the data frame as well. We'll just have a look at the first few. There we go. So we got 1, 2, yeah, all very, very high, because the thing is, this data is very easy. It's a very nice set, and that's partly why I picked it, because it's a very pretty set and it has nice clear domains. So line plot, we're just going to create a nice seaborn. So seaborn was imported as SNS. Line plot where our data is coming from the KA data frame, and the X is going to be equal to K value, sorry, and the Y is going to be equal to accuracy. Let's have a look at that. So you can see here that around 12 is considered to be really good. Of course, we can just keep running this multiple times and you'll see it shift slightly. So if I run this again, there we go. So now it's around 11. So basically around this 11-12 margin, we're getting some really, really good accuracy. And that's where you'd want to set your K value, so you can find the best K value to use in your model. And I suppose that would be the way that you would say you're training your K nearest neighbours algorithm. I was going to explore different ways in which we can classify neighbours and assign weights to certain neighbours in certain positions, and how we can use that to really, really start getting some nice results and some powerful predictions. However, this video is getting quite long. So if you would like me to explore that, the area of effectively using a different function than just mode to weight what your prediction is going to be, then please comment below and I will think about how I'm going to pull that video together. Otherwise, I think we've done a pretty in-depth study of the kNN algorithm. You've coded everything up from scratch. And there's just one small thing that I'm not going to do on video, but it would be very good for you to do to tidy things up nicely, is to take these two functions that we've written here and add them in to the kNN modules file. So then we can just import them directly into any projects you're working on. I know this has been quite a long video, but thank you so much for watching, and I hope it was really useful. If you like this kind of content, why not subscribe to the channel, and I'll put some other videos up you might find interesting. Anyway, hope to see you in the next one. Bye!